Mathematical Decision-Making, Network Models, Beyond Euler Circuits, Lesson 4 for Edmodo Group. The learning goals for Lesson 4 include being able to Eulerize graphs, to compare Eulerization of graphs, to use techniques which will find a best Eulerization, and to apply the Eulerization of graphs to real-world situations. First, let's stop and do a brain activator. Refer to the graph at the right. Jot down the following. A. List the vertices. B. Find the valence of each vertex. And C. Is there an Euler circuit for the graph? Explain how you know. You may want to pause the video to answer these three. Now let's do a quick check to see how well you performed. For the first one, A, list the vertices. We know that the vertices are A, B, C, D, and E. For B, find the valence of each vertex. We have 2 as our answer because as you look at each vertex, there are exactly 2 edges that are connected at the vertex. And for C, is there an Euler circuit for the graph? Yes. We know that there is one because the graph is connected and all the valences of the vertices are even. How did you do? Today we're going to go beyond Euler circuits. We're going to apply Euler circuits to real-life, real-world situations. So now let's see what Euler's theorem tells us about the 3-block neighborhood with parking meters represented by dots in the diagram below. Notice that we have streets in between the blocks. There's a street that goes from B prime to F prime, and the width of that street is shown from the distance from B prime to B double prime. In a similar way, we can look at C prime and G prime and C double prime and G double prime. That area indicates that we have a street. Also notice that there are no parking meters along one of the sidewalks, C prime, G prime. We can create a graph to represent this situation. What we're going to do is put B prime and B double prime, F prime and F double prime together to form the distinct vertices B and F. We can do that because B prime and B double prime represent one street corner. They are merged in the graph to form the vertex B. The same would be true for all the other vertices. Because we use edges to represent only sidewalks along which the officer must walk, the sidewalk with no meters is not represented by any edge in the graph. Notice that the sidewalk B prime, F prime has meters, and B double prime, F double prime has meters, and therefore we have 2 edges that connect B to F because the officer has to walk along each of those sidewalks. Now let's take a closer look at this diagram. If the officer is going to patrol all the meters, he's going to have to reuse some of the edges in this graph in order to cover all of the circuit. For efficiency, we need to keep the total length of reused edges to a minimum. This type of problem is often called the Chinese postman problem. The problem was first studied by the Chinese mathematician Meigu Guan in 1962, hence the name. Although it is called the Chinese postman problem, it can be applied to many different situations in which the graph would represent something similar. And in our case, the graph is representing an officer who is patrolling parking meters. We're going to solve the Chinese postman problem and use it to discuss applications beyond parking control. We know that in a realistic Chinese postman problem that the lengths of the blocks would differ as far as the width is concerned. So in a realistic problem we would have to consider the lengths of the sidewalks or whatever the edges represent, because we want to minimize the total length of the reused edges. In other words, we want to reduce how much the postman or the patrolman will have to walk as he is doing his assigned job. We're going to make it a simplified Chinese postman problem by supposing that all the edges represent the same length. And we know that that isn't truly the case because often the length of a city block is different from its width. But in this case, we're only going to count the reused edges and we will not have to add up their lengths. To solve the problem, we want to find a circuit that covers each edge and that has the minimal number of reuses of edges already covered. Now, looking at our graph, we know that it has no Euler circuit. But there is a circuit if we reuse one of the edges. So we can start at A, then go to B, C, D, H, G, C, back to G, F, B, F, E, A. Let's draw this circuit so that when CG is about to be used, we install a new extra red edge in the graph for the circuit. As you draw yours on the assignment today, you can either use a colored pencil, a pen of a different color than the ink on your paper, or you can use squiggly lines to indicate that you've added an edge. By duplicating edge CG, we can avoid reusing the edge. To duplicate an edge, we must add an edge that joins the two vertices that are already joined by the edge we want to duplicate. This is not a new edge. It is one that is reused. Now, we can clearly see as we go through the circuit how the circuit is made. So in this case, the cost or the length of the circuit is 12. We just Eulerized a graph. Eulerizing a graph is the process of adding edges that duplicate existing edges of a connected graph so that all valences are even. So let's look at how to do that. We're going to add edges by duplicating existing edges until we get a graph that is connected and all vertices have an even degree. Then we're going to find an Euler circuit on the Eulerized graph. And then we're going to squeeze this Euler circuit by reusing an edge of the original graph each time the circuit on the Eulerized graph uses an added edge. Now, our next example is going to help us make sense of these how-tos and definitions. So, let's go through that process of Eulerizing a graph. Here we're given a graph with 4 vertices. It has 5 edges. And the first thing that we have to do to Eulerize the graph is to locate the vertices having an odd degree. As you look at this graph, it's easy to see that there are 2 of those, vertex B and vertex C. Next, start at one of these vertices and duplicate an existing edge. Here I've done 2 duplications because I wanted to make sure that both B and C have an even balance. So I duplicated edge BA and then I duplicated edge AC. Now the graph is all connected and each of the vertices has an even valence. Our next step is to find an Euler circuit. The numbers and the arrows indicate the circuit. So to do this, I would go from A to C, and then C to A to B, B to D, D to C, C to B, and B to A. Right, so notice that this particular circuit has a value of 7. It has a cost of 7. Finally, we want to squeeze the duplicated edges to their corresponding edges. And in other words, we're just going to indicate with the arrows the direction in which we're traveling on the existing edge. So the duplicated edges in this final diagram have been squeezed together with the existing edges that they correspond to. In general, if you add the duplicated edges correctly, the number of reuses of edges equals the number of edges added during Eulerization. So you can see that we added 2 edges in our Eulerization process, and so the number of reuses is 2 because we reused the edge BA and the edge AC. Why duplicate and then squeeze? Why not just add a new edge instead? So here I've decided that because B and C are the 2 odd valence of vertices, that I could just create a new edge that joins B and C. Remember that the edges represent connections between the objects in our network. These connections may be streets. They could be cables, a variety of different things that these connections could be. A garbage truck, for example, will have to travel on the existing streets. It cannot simply make its own path. Let's look at a case where the odd valent vertices are more than one edge apart. In this particular network, we can see that X and Y are separated by several other vertices. As we discussed earlier, we can't simply connect X and Y with a new edge, because that would be creating something that doesn't exist in our network. However, we can connect X to the adjacent vertex, U, because they're already connected. And then we can connect U and V, adjacent connected vertices, and we can connect V and Y. We're actually duplicating those particular edges in order to be able to Eulerize this network. We want to get an Eulerization with the fewest added edges. Remember, we want a best Eulerization to minimize the retraveling edges where the work has already been done, because it saves time and money in real-world applications. Let's look again at the example that we worked with earlier. In this case, we had duplicated edge BA and edge AC. You may have already noticed that edge BC would be a better Eulerization of this particular graph. By connecting, or by duplicating the edge BC, we have only added one retracing of an edge, whereas earlier we had two. And now we can see that we have reduced the cost of this particular circuit. Again, to indicate that we have squeezed together the duplicated edge, you'd simply draw the arrows and number to indicate the path through the circuit. Now, as network graphs get bigger, finding a best Eulerization becomes a real challenge. A systematic procedure does exist, but it gets complicated. We're going to look at a procedure to find a best Eulerization for a common network, a rectangular network. So first, let's define what a rectangular network is. A rectangular network is composed of a series of rectangular blocks that form a large rectangle. An example is given below. A rectangular network could model a section of city blocks or a neighborhood. So let's look at some best Eulerization examples. First of all, here's a 3x3 rectangular network. Now, as we look at this, we can see that because there are some odd vertices in this diagram, even though they're not labeled, those are going to require duplication of edges in order to be able to traverse this circuit. So here is a best Eulerization way to do that. Let's look at another, a 3x4 rectangular network. Notice that there are 3 stacks of blocks and 4 columns of blocks. That's the reason we're referring to it as a 3x4 rectangular network. A best Eulerization for this particular one would be a diagram like this. And finally, a 4x4 rectangular network. We have 4 rows and 4 columns of rectangles forming the larger rectangle. A best Eulerization example of this is this one. Now, you might wonder, well, how do you get those? How can you find a best Eulerization example? In order to do that, we'll use the edge walker technique. Starting at a corner, travel in a direction. Let's start at the corner labeled A, and let's travel along the edges in a clockwise rotation. It doesn't matter which corner that you choose to begin, and it doesn't matter whether you choose to go in a clockwise or counterclockwise rotation, but you are going to be walking around the edge of the network. So, we're going to add edges using the following rules. If the vertex is odd, we're going to link it to the next vertex by putting in a duplicated edge. Then we're going to check the valence of the next vertex. If it happens to be even, we'll skip it and move on to the next vertex. If it's odd, we're going to link it to the next vertex. So let's take a look at how this is accomplished. We're going to start at vertex A, and notice that vertex A is even. Moving in a clockwise direction, we go to this particular vertex. And we can see that this vertex happens to be odd. So the rule is, if it's odd, we're going to link it to the very next vertex with a duplicated edge. Move to that vertex. Check to see how many edges are connected to it. There are 4, so its valence is even. We're going to skip it, move to the next one. Notice that there are 3, so we're going to have to add. Move to B. B has 1, 2, 3, so it's odd. We're going to have to add. Move to the next one. Has 1, 2, 3, 4. It's even, so we'll move to the next one. 1, 2, 3. It's odd, so we're going to have to add. Check D. 1, 2, 3. It's odd, so we're going to have to add. Check the next one. 1, 2, 3, 4. It's even. Skip. Next one. 1, 2, 3. Odd. So we'll add. And we continue to do that as we move around the figure. We're just walking the edge. So now this vertex has 1, 2, 3, 4. So it's even. C is even, and then the next vertex is odd, so we'd add. This gives us a best Eulerization for a rectangular network. There is not an easy way to know how many edges to duplicate in order to find a best Eulerization, but here's a rule to use. In a best Eulerization of a graph, the number of edges that must be duplicated is at least the number of odd vertices divided by 2. So what this says to us is the minimum that you must add. It doesn't exactly give us the exact number to add. Let's take an easy example, one of the first that we looked at today. Now remember that we found a circuit by duplicating this in several ways. The first time we did it, we had duplicated BA, and then we duplicated AC, and if you recall, that gave us a value of 7. It took us 7 moves in order to get through the circuit. But we found a better Eulerization by connecting or duplicating BC. Now notice that in this particular graph, B is an odd vertex, C is an odd vertex. So if we take the number of odd vertices, which is 2, and we divide by 2, we get 1. What this helpful hint tells us is that we know that we must have at least one duplicated edge in order to have a circuit, an Euler circuit. And we know that we found that by duplicating BC. Of course, we want to optimize, and Eulerizing a graph in an optimal way will help us reduce costs. For an unweighted graph, that's just assuming that all of the edges are the same length, the cost of traveling through the circuit is found by adding the total number of edges in the graph to the total number of edges duplicated. In this case, there are 5 edges in the graph. One of those edges was duplicated, so the total is 6. Now, there are many possible Eulerizations, and we know that we want to pick a better or a best Eulerization. As we look at more complicated graphs, the problems become more interesting, but they become more challenging as well. In this particular graph, the vertices that are labeled are the vertices in the graph that are odd. We know that to Eulerize, we want to look at the odd ones, and we duplicate existing edges in order to create our circuit. One possible way of moving is to connect X and Y. And remember, we can't just simply draw a path from X to Y. We must go along already existing edges. So here's one way, and it takes us 5 repeats in order to get from X to Y. Another way would be to move only 3 repeats from X to Y. So now let's go from W to Z. Notice as we choose this particular path that we have 6 repeated edges. But suppose that instead of moving from X to Y, we moved from X to Z, and then we connected W and Y instead. Right, this particular diagram shows that sequence. We could actually even make it fewer duplicated edges if we connected X and W and Y and Z. Remember that our helpful hint only told us that there would be at least 2, and it turns out that it's more than 2. In order to make this both a connected graph and to have all of the vertices with an even valence. In this lesson, you have learned to Eulerize graphs, to compare Eulerization of graphs, to use techniques which will find a best Eulerization, and to apply the Eulerization of graphs to real-world situations. You will now work on some exercises which will help you review and apply what you've learned in the lesson.